Okay, so we need to make sure we understand what intermolecular forces of attraction are. Write this down, please. Intermolecular forces of attraction. All right? So there's actually two prefixes here we're going to talk about today. Intra and inter. Intra and inter. What's the difference? Intra versus inter. Intra is within. You're right. Intra is within. Inter. Out and everywhere. Hold on, I'm just going to take apart my CO2 here quick. Hopefully not hurt myself. Okay, here we go. There we go. Wait, what am I doing? There we go. What are these? Water molecules. This has intramolecular forces. That is an intermolecular force. So intra, inter. Stand up, Ben. Please. Sorry. I'm trying to be polite. Intra, inter. What's the difference? Intra,
Separated and then
inter.
together.
So what's an intramolecular force called? This has intramolecular forces. What's holding this together? Bonds. A bond is intra. What holds me together? What holds him together? Our head, our legs, our arms. They're attached to our body. They don't just fall off. Okay? There's forces and bonds and muscles and tendons holding our body together. Those are really strong. When we shake hands, that's between us. That's inter. That's a lot weaker. We can let go a lot easier than we can rip our arms off our body. Okay? So this has intra bonds, this has intra, but the oxygen here is attracted to the hydrogen here. That attraction, it's hard to show that. That's why I have the videos. That attraction here, imagine there's attraction between these two. That's called intermolecular. So inter means between two. Intra is within one. I like how you said that. Within one. Let's make sure we're clear with that. Let's write that down. Intramolecular. So we'll actually do exactly what I just did there. We'll take two water molecules, okay, put a dotted line between the O of one and the H of another. That dotted line is called our put inter in quotes, molecular force. And that is weak compared to, and we'll label this bond right here, that is a bond, a chemical bond, a polar bond, which we've already learned, and water is polar. That's a bond, and that's called an intramolecular force. And that's strong. So bonds are strong, forces are weak. Again, what's holding them together, what's holding me together, is way stronger than our handshake. Okay? It's easy to shake hands and then let go. Even if, Ben's pretty strong, I'm fairly strong. We're going to hold on tight. I think some of you in here eventually could rip us apart. If enough of you grabbed Ben and me, we would not be able to hold on. Because it's just a handshake. But I don't think anyone here can rip his arm off his back. And good luck trying. Because someone's going out a window and it's not going to be him. All right. So the concept is the bond is strong. The force is weak. However, this may make sense to you. However, there's 4 types of these, and they are ranked in strength. So some are really weak and some are really strong, but they're all considered weak compared to bonds. Trying to be clear, not confusing. But what you've already learned about, metallic, ionic, covalent, that's strong bonds compared to forces. So what holds H2. What holds that together, that bond, is stronger than a force between two. All right, I'm really trying to repeat myself over and over again. I took apart the other one. So that's what we're learning here today, and that's when I rubbed the balloon and stuck it on the wall, and then we poured the water on Thomas, almost. All right, and the water didn't come out. Why? It's actually this force right here, the force holding water together. What did we say that was yesterday? Hydrogen bonding, right? That's hydrogen bonding. That's a hydrogen bond between an O of one and an H of another. Not the actual bond. The force is called a hydrogen bond. I know that's confusing. We'll get to that in a little bit. All right. Makes sense to most of you, hopefully? Everybody with me here? Okay? All right. So one more thing I want to write before I list all the forces and get into the videos. I use the videos to teach. I have a video for each force. Before I do that, give me a star here. Physical states. What does that mean? What's a physical state? Solid, liquid, gas. Physical phase, physical state. So S, L, or G are dictated by, or maybe I should write depend on. Either way, depend on or dictated by intermolecular forces of attraction. Intermolecular forces of attraction. So, how close the molecules are to each other dictates whether it's a solid, a liquid, or a gas. You already learned this, but now I'm just taking what you've learned and what you know and applying it to the new material so that you can put it all together in your brain. Okay, so intermolecular forces are responsible for how a substance looks. Okay, if Ben and I shake hands as far apart as possible, we could call that a gas. If we get really close together, that's a solid. So depending on how strong that handshake is, how strong that force is, it changes their physical state. So if these two are really close together, solid. A little further apart, liquid, and then really far, gas. And I'm just trying to get you to understand it's the forces that affect that, not the bonds. Because this molecule and this molecule are what they are. It's how close they are is solid, liquid, and gas. Which also brings us to phase changes. Phase changes, and you learned this a long time ago, especially with table H with those four curved lines. The higher the boiling point, the stronger the forces of attraction. I think a lot of you memorized that, and that's good. Phase changes depend on intermolecular forces of attraction. Intermolecular force. I get tired of writing that, so I might just start writing IFOA. Yeah, intermolecular forces of attraction. Intermolecular forces of attraction. IFOA. You've already learned that. If something has a high boiling point, it's because it has strong forces. If it has a low boiling point, it has weak forces. So I'm not going to get into details there, but that's kind of the summary of why we're learning this stuff. All right. Honkobriffs. Most of them are what phase? You can look over there. Most are what phase? Gas. So that means they're weak or strong? Weak. They have a force that is a very weak force, and that's the first force I'm going to talk about today. And that's the same force that held the balloon on the wall. All right? Didn't I whack the balloon off the wall?
Yeah.
It's easy. I could just flick it and it would come off. It's a very weak force. Okay? But I can't split, and I can't take my hand and separate water molecules so I have steam. I can't take water and turn it to steam. That's a lot stronger. I need to heat it up to do that. So I'm trying to kind of start you thinking here of the strength of these forces. So there's four types. The weakest is London dispersion forces. London dispersion forces. That's the first force and is the weakest. Everything in the world has London dispersion forces. All right, corny Star Wars joke. It's called the Force. So everything has London dispersion forces, but nonpolar, like aquabriffs, hydrogen gas, for example, only has dispersion forces. That's why it's a gas. It's so weak. Water has dispersion forces and hydrogen bonding, so it has two forces. This just has dispersion. Those are weak. I'm going to spend the most time today talking about that. These are a little confusing. I did the best I can, got the video. Hopefully you'll be good. Next, after London dispersion, we have dipole interactions. Where have you learned or heard of poles or dipoles? in lab and in class? Who has it? Polar molecules, right. That's stronger. Dipoles are stronger than nonpolar. So this is for polar, this is for nonpolar. I'm going to give you notes on each one. I'm just listing them right now. After that, if you dissolve salt in water, you have what's called molecule-ion attraction. In fact, anytime any ionic dissolves in water, it's because like dissolves like. This explains it, molecule-ion. So we'll get to that. I have a video that shows that. And then the strongest force of attraction is hydrogen bond. Hydrogen bonds. That's the strongest. That's the strongest type of force. That means high boiling points. Water has a pretty high boiling point compared to other covalent compounds. Water boils at 100, that's pretty high for covalent compounds. All right, so there's your forces. Let me get to the videos here, and then we'll move on here.
With more notes?
With more notes, yes, lots of notes today. All right, lights please, Tristan. And here we go. Not doing it.
Too easy.
Yep. A little tired. All right. So first one, London dispersion forces. Here we go.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 16. It's on London dispersion forces, which were first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here. But before we move on and talk about it, think about the forces in this picture. Which are greater, the forces within the individual people holding their atoms together, or the forces between them holding them together in this photo? Well, clearly it's the forces within your body. And so this is the first video in a set of videos that talk about bonding between molecules and within molecules. And so if we think of them all as molecules, and we move them apart a little bit, they're going to be the intermolecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular, within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive forces. These are intermolecular, between molecules. And they're going to be found in all atoms and molecules. So everything is attracted through London dispersion forces. It's really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole.
Okay, so in your notes, what you are writing is what he just said. This is a little confusing. I like it because it's organized, but I'll tell you what you need to write. Here's what you're writing. So London dispersion forces, sorry, let's title that, London dispersion. All right, so you got your list, but now we're going to go on each one in depth. All right, London dispersion forces. This force is created by electron movements. Electron movement. And temporary dipoles are formed. So that electron cloud outside the nucleus, electrons are always moving. Well, sometimes all the electrons tend to be on one side of the molecule, making it partially negative. Hey, what's going on?
Hi.
You came here with our friend?
Yeah, with Zach?
Yeah.
Yeah. Did he stop in?
Yeah, I saw him downstairs.
Yeah.
Yeah.
But I'll catch you sometime not in class.
All right.
See ya.
Good to see you. So the electrons get to one side of the molecule, and that molecule becomes partially negative, that side, and the other side becomes partially positive. So in other words, you have an atom or molecule. If all the electrons line up here, then there's none over here. This is partially negative, that's partially positive. That's a dipole, but it's temporary because the electrons can shift and now come back over here. Don't draw that. But that's what temporary dipole means. So that dipole we're doing in lab, it can shift and change with these forces, which is why it's weak. It's not permanent, it's weak. Kind of like the balloon on the wall. It's not going to stay there forever. It's temporary. Okay, so let him continue to talk.
Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding.
Take AP Chem, we learn about all that. But in Regents Chem, all you need to know is the temporary dipole and really this one. What's molecule size? Means more electrons. So this is created by electron movement, which is temporary dipoles are formed, and more electrons means stronger forces. More electrons results in stronger forces. If electron movement creates the force and you have more electrons moving, it's going to be a stronger force. That should make sense if you're paying attention and trying to learn this. So based on electron movement, how the electrons moving outside the nucleus, and if you have more of them, you're going to have more forces. That should make sense. So if you look over on the periodic table, hopefully this will work. Okay, how many electrons does iodine have? How many electrons? 53. What physical state is it? Solid. It's black, so it's solid. Okay. How many electrons does fluorine have? 9. What physical state is it? Gas. It's not a coincidence. Less electrons, weaker forces. More electrons, stronger forces. So even radon down here, it's a very dense gas, low lying near the ground. Helium is one of the least dense gases. Why? You got 2 electrons, hardly any of these forces. Radon has 86, lots of forces. Just trying to give you an example there. All right. So now what he's going to do is going to show you this temporary dipole. I'll pause it. You're going to draw what you see.
Which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase is going to be these London dispersion forces. So right here I have 2 helium atoms, and so they're going to have 2 protons on the inside, 2 electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are 2 what are called temporary dipoles. They have
Okay, so he says a lot of stuff, and I understand where you're at in your life. A lot of it's going right through your face. You're not listening or really learning all of it, but the important stuff I'm stopping and explaining. So I'm not talking down to you, don't take it that way, just focus on what I'm explaining. He's saying a lot of stuff you don't need to know, and you're probably not grasping anyway. This you need to know. What's a temporary dipole? It's when you have those partial charges. This should not be new. We've been doing this, and in lab I'm really having you focus on it. This happens everywhere all the time. The air in this room, sometimes 2 air particles come together and they just go past each other. Sometimes this is created and they stick. They stick together temporarily, then they break apart. This is not a permanent force. It's very weak, and air doesn't. Gases do this. And here's what happens. When the particles get close together, sometimes the electrons migrate. So if they're all on this side is partially negative. Well, that side doesn't have any electrons, so it's partially positive. This one does the same thing. So that attraction between these 2, that's your dispersion force. The positive of one and the negative of another. That's called the dispersion force. So if you have, and they show it with a dotted line, if you have more electrons doing this, those charges become stronger. So if you have 2 electrons like helium, this force is going to be weak. But if you have 86 like radon, these partial charges are really strong. And strong is relative. Really strong compared to helium. It's still a weak force, but stronger than helium's. And that's what dispersion forces are. So kids always want to know, what do I need to know for the test? Are you going to have to draw this? I highly doubt it, but you could have to explain it. I can see a question where you'd have to explain dispersion forces. So that's one way to do it. The other questions that I see on dispersion is what type of molecules have it. They'll say, which of the following has dispersion? The answer is nonpolar. So we're going to write that down too. nonpolar molecules have dispersion. Nonpolar molecules have dispersion forces. All molecules and atoms have dispersion. He said that. But if it's polar or if it's water, it's going to have multiple forces on top of dispersion. Nonpolar, like the Hunkelbrick, they only have dispersion. Okay? Only dispersion forces. And there's two more things that I want to talk about, and I already kind of alluded to it. Again, eyes over here. As we move down these two groups, 17 and 18, the number gets bigger, so the forces get stronger. That's a Regents question that's pretty common. It'll say, which of the following shows an increase in dispersion forces? And they'll put it in the right order, F, C, L, B, R, and I. Then they'll flip it around. They'll go I, C, L, B, R, F. Then they'll go I, B, R, C, L, F. Then they'll go C, L, F, B, R, and I. They'll move them all around. You got to go down, and the ones at the bottom have more electrons, so they're stronger. So that's what we're going to write. Then we're going to move on to the next force. So the last two things to write here, we have moving down groups 17 and 18. Moving down groups 17 and 18. Dispersion forces increase or get stronger, whatever you want to write, due to increase in atomic number. And atomic number tells us the protons and electrons. So I'm being a little vague, but I'm doing that on purpose. I need you to remember atomic number tells you the number of electrons. So I'm kind of reviewing that with you. Really what it means is you're increasing the number of electrons. That's what that means. You with me, Cody?
Yeah.
Good. I know a lot of this is confusing. It's weird stuff. Okay? I get that. And I can't physically show you this. The balloon was the best I can do with a dispersion force. The best I can show you. So it is hard to show this, hard to see it. So I try to show you some animation. That's the best I can do to see it. So we're moving on. That's dispersion. Next on the list is dipole interaction. Here we go.
Bless you.
Bless you, whoever that was. Dipole interactions, which you already know about, sort of. So dipole interactions. Dipole interactions. All right, put a little star. Only polar molecules. So I just talked about nonpolar, that's dispersion, and really weak. Polar tend to be liquids and solids. They are stronger. Their phases are liquids and solids, particles are closer together. What is a dipole interaction? I don't like the way this person talks, so I'm just going to click and stop. All right, there we go. So it's really just this image with someone talking and drawing on it. So I can do that. I don't need them to do it for me. This is HCl, hydrochloric acid. If I had a whole tub of hydrochloric acid, it's a liquid. Why is it a liquid? Because this, which is called a dipole interaction, so copy this down. This dotted line, that's your dipole force. There's a dipole on each molecule, which you learned about. The electronegativity difference, pulling the electrons, that positive, negative, and this is very similar to dispersion, but this is permanent. So that's a permanent dipole. So I'm going to write that here. You can put it under your picture if you want. This is a permanent dipole. Not temporary, it's permanent. That's why it's stronger. So I'll copy this down in our notes as well. So we have HCl attracted to another HCl, and that's because of these dipoles. I'm going to label the dipole. I want you to as well. Label that arrow. It's good practice. Positive, negative, positive, negative, and again, there is your dipole. Okay, I'm going to label that dipole force. That's the dotted line between the Cl and the H. Intermolecular attraction. Again, they say weak. Yeah, weak compared to a bond, but stronger than dispersion forces. So that's a dipole interaction. Dipole is not as, there's not as much to it. That's it. We're done. That's all I'm going to give you. And then your homework. And then tomorrow I'll get the whiteboards out. We're going to do some practice problems where I will say, okay, you have 2 molecules of HF. Show the dipole interaction. So you're going to take what you learned today and on the homework, and then you're going to do it on the whiteboard. That's how we're going to learn it. not just writing this down and memorizing. That's not going to really work for everybody. So we'll practice tomorrow. All right. But anyways, that's dipole. Why? Two polar molecules attracted using those partial charges. That's called your dipole interaction. Okay. So there's your dipole. Hopefully you guys are still with me. Ion dipole is next. What do we got for time? 4 minutes? Oh boy. Oh wait, no, we get out 28 or 26?
28.
28. Oh, let's get stepping here. Alright, molecule ion. Alright. Molecule ion attraction. Alright, so this little star is when ionics dissolve in water. That's the easiest way to explain it. When salt dissolves in water, that's not what I want. I want this one. Watch what happens. I know I'm going quick, but stay with me.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride.
Okay, so they should leave this up, but they don't. The green is Cl minus and the white is Na plus. Try and keep that straight. Keep watching.
And ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions.
Okay, so the water comes in and rips the salt apart, piece by piece. The Na gets pulled off, the Cl gets pulled off, and then more water would pull this one off, more water would pull that. So it gets ripped apart piece by piece till it all dissolves. Now you have ions floating around, so it conducts electricity, right? So I'm trying to connect to the lab there. Oxygen is partially negative, so it's attracted to the Na plus. Over here, you see these little white ones. Hydrogen is partially positive. It's attracted to the negative Cl minus. So that is what this attraction is. So I'm going to draw this in our notes. It's not really a whole lot of notes except the picture. Here's how we do this. I want Na plus, and then leave a space and put Cl minus. You're going to draw water surrounding it, just like this picture here, or this video. So around the Na, I'm going to have all of my oxygens facing the Na. And then all my hydrogens, right, I'm going to do my Mickey Mouse, all the hydrogens are facing out. So I want you to draw this. And again, the reason for that is because water is polar, and the oxygen is partially negative with that dipole. And so hopefully some of you or all of you are seeing the order I teach and you learn things. It makes sense, so when you get to this, you don't have to learn everything at once. You know what polar means, you know what dipole means, you know what the partial charges mean, now you just have to apply it. Hopefully that's making sense. And then with the Cl minus, it's the opposite. Now the hydrogens are facing the Cl minus because they are partially positive. All right, they will be facing the Cl. That happens every time you dissolve salt in water. In fact, anytime you dissolve anything in water, water is doing this. It's ripping the crystal apart, whether it's sugar, salt, whatever, and it is based on similar attraction, like dissolves like. All right, last thing with this, and I'm going to have to call it. We're not going to get to hydrogen bonds. Hold on, I got to write one more thing. But as Curve said, the answers are in the book anyway, so you can do it. Just label your partial charges here. Oxygen is partially negative, and then the hydrogens are partially positive. Label those weird little squiggles. And that's why water does what it does. That's why it surrounds Cl and Na the way it does. Those opposite charges are attracted to each other. All right, that's called molecule ion attraction. Pretty strong, but how do you separate salt from water? So you have salt water, what would you do? Evaporate the water, right? So it's not that hard to separate. It's strong, but it's not as strong as a bond.